Dobar dan. Thank you for having me here. My name is Oleg. I work in Yandex, and I spent last decades with distributed systems and with databases. I'm crazy about open source, and I'm really proud to be part of YDB team and participating in YDB open source release. And let me introduce to you YDB. YDB is an open source distributed SQL database, as you can read on the screen. We built it from the scratch in Yandex. It has been developing since 2014. It's written in C++, and it's fully in-house development. Main characteristics of the system, it's those that it's, first of all, it's relational database, and it provides traditional ACID transactions, SQL, a convenient SQL interface. It's strongly consistent systems from CAP theorem points of view. In case of partitioning, we prefer consistency. And in practice, we deal with huge workloads. So one of our main goals was almost linear and horizontal scalability. So our major clusters consists of thousands of servers, and we can deal with millions or tens of millions transactions per second and with petabytes of data. Another goal to create in-house database was to build highly available database that can run even after huge failures. For example, vast majority of our clusters lays within 3 availability zones, and it can work even after one availability zone goes down. And it works automatically. It's available both for reads and write throughputs. As far as most of our services works directly with customers, they're interactive, so we need to provide 0 downtime for database. And database architecture provides ability to create not only relational database, but many of applications such as topics, distributed queries, monitoring, network block store, etc. So using blocks of the system, we can build many different systems. A year ago, we published all our source code on GitHub, and now it's fully available. Whole source code, documentation, our SDKs, everything available on GitHub. I would like to reveal some key concepts behind the system in order to provide you with the things that make it possible to build a reliable, fault-tolerant, scalable, and strongly consistent database. So, physical architecture is quite simple. We use only commodity hardware, so only arbitrary set of servers within the cluster. And we use shared nothing architecture, so we divide data into chunks, and each server responsible for its data chunk. We tend to create flexible system. We want to make it possible to grow storage and compute layers independently. So as in most modern databases, we disaggregate storage from compute. And if we take a look at logical architecture, all layers, such as storage and compute, use our network layer called interconnect, and they communicate through interconnect. As far as its in-house system, we built our API, public API, and we have application team who is in charge of developing SDK for YDB. And during my speech, I will try to reveal some aspects of communication between our API and SDK, because when we talk about distributed systems, it's not a matter of only server side, but it's both about interaction between client side and server side. As you can see on this slide, within computer layer, there are some strange things called tablet, and there are many tablets here. And let me tell you about tablets. So tablet is a core component of the system. It's a set of C++ classes. It's the only component of application layer who has its persistent state. Tablet provides with an API. Tablet can provide different APIs for the upper layers. For example, if we talk about a relational database and tablet act as a part of table, it can provide API such as read or select, insert, update the row. You can think about tablet as an adapter. It's a real adapter to the distributed storage, because tablet stores all its data within the distributed storage. But tablet may have a volatile cache in order to increase throughput or decrease latencies when you read the same portion of data from the tablets. And tablet writes its own write-ahead lock to the distributed storage. And tablet is a very lightweight entity. It can easily die and start on another application node after any failure. Inside table, we have replicated state machine, and it writes its changes to the distributed storage, and on the crash, it recovers all the data from the storage. And replicated state machine provides guarantees similar to Raft protocol. Data organized like log-structured merge tree, and tablet guarantees ACID for the data. Tablet has small application layer, and you can easily rewrite it and implement different things like topics, tables, time series, etc. So you can use the whole infrastructure and write only simple application code, and you will have a different purposes system. And main thing is that tablet stores its data in reliable and redundant distributed storage. There are many tablet types reusing those application logic layer. So one of the simplest tablet is tablet data shard. It stores a set of rows, like a range of rows of tables. There are another tablets, there are data tablets and system tablets. So everything within YDB is a tablet. There is such component like scheme chart. It's a special system table who is responsible for metadata, for schema, for gathering and collecting statistics from data charts, etc. There is special component called Hive who is responsible for tablets balancing. And there are more different tablet types responsible for all the parts of the system, like for distributed storage, for distributed transactions layer, etc. How we achieve scalability? In distributed system, one of the main approaches is partitioning. So YDB table, I will show an example of the table, but almost the same with the topics and other different types of tablets. So YDB table has its own primary key. It's obliged to have a primary key. And rows are ordered by primary key, so you can deal with it like with index. And as far as table size can grow up to petabytes, we split table into different parts. by key ranges. And those parts, for each of those parts, responsible single tablet data shard. We can split tables by workload, by throughput, or by size, or simultaneously by load and by size. And simultaneously, we can merge tables if we gather statistics and we understood that there is no more workload, or you deleted all the data, and on the compaction process, tablet was shrinked, so we can merge neighbor shards in order to keep to make it smaller amount of tablets. And we tend to evenly distribute all the shards through all application nodes in order to keep everything within the cluster evenly loaded. Besides that, we provide vertical partitioning, so not only horizontal but vertical. So when you use column families for different set of columns, you can, for example, put different columns on different storage types. So you can put, if you need fast key value access, you can put your primary key on solid state drives. But if you want to keep your system economically efficient, you can put such data as, for example, huge JSON documents or base64 encoded images on rotational drives. And moreover, if you know the nature of your data, you can use different compression strategies for different column families. I mentioned distributed storage when I talked about tablet. So tablet stores its data in distributed storage, and distributed storage is responsible for redundancy. So let's talk about distributed storage, what it really is. Distributed storage, it's a storage of immutable blobs of various size up to 10 megabytes, and it's designed to be fault-tolerant. Moreover, distributed storage has its own guarantees. It guarantees that you will give success only if your blob, all your blob parts are recorded successfully on all hard drives. Otherwise, you will have an error. And distributed storage provides you with different configurable, with different redundant configurations. We have our major configurations are mirror 3DC, so it's configuration for 3 availability zones for clusters who are in 3 availability zones, and it can survive availability zone failure and single rack in another availability zone failure. And another example of redundant configuration, a block for 2. This is for single AZ clusters. It can survive 2 servers failure simultaneously. Distributed storage consists actually from the hard drives installed in servers, and we divide it into so-called storage groups. You can see it on the picture. So we take different hard drives within different servers placed in different racks in order to be in failure model, and we splice those hard drives onto little parts onto virtual devices, and those virtual devices makes a storage group. So if we take a look at distributed storage internals, it has its own layered architecture, and it consists of 3 main components. P-disk, so it's physical, it's code that is responsible for working with bulk device. V-disk, it's virtual drive, it's a slice of physical drive, and one of the key components is distributed storage proxy. Physical drive, so P-disk, this is the code who works with bulk device. It's optimized for recording of small blobs on the drives. We have many different optimizations, for example, for rotating drives or for compaction on solid-state drives. We bypass all the caches while on the writing. So we disable all the caches. And in order, as far as we slice a physical device onto logical slices, we wrote our own fair scheduler who provide fair throughput for each disk slice. For example, if we slice hard drive into 8 virtual devices, we guarantee that each of the 8 devices will have its own fair 1/88 throughput. And virtual device, it's key value storage, and it stores parts of the blobs. It provides many interesting features like automatical replication between different virtual devices. It can recover after failure and after that data loss. It synchronizes all the meta information between virtual devices within one storage group. And as far as we tend to make system convenient not only for our clients but for YDB programmers, we wrote such component as distributed storage proxy. It makes working with distributed storage very convenient because tablet works only with one distributed storage proxy instance, and it has very simple API. So all complexity of the logic of storing redundant data incorporated within distributed storage proxy. It provides simple get, put, and so on API. Distributed storage proxy API, I will review some of, as an example, some of its API calls, like put, get, and block, because it's, from my point of view, it's quite interesting. For example, if we want to put some blob into distributed storage, what we have to do? I will show it on using example block for 2 schema with Erasure coding. So what we need to do? We need to slice blob into 6 different parts after Erasure and write it to different drives. And only when all 6 parts are successfully written, we can answer with success for the tablet. We have 2 extra drives as a handoff in case of failure, so we can survive 2 drives failure. So let's take a look at the picture. For example, we want to, so tablet, not we, but tablet want to put some drive to the distributed, some blob to distributed storage. So we slice blob into little chunks, into little parts. We calculate, so we understand on which, by hashing, on which virtual devices we will put parts of the blob. And if everything works fine, we just write all those parts on the virtual devices. But in case of failure, for example, we lost 2 hard drives with its slices, we must write on handoff drives. So we must wait for all 6 parts to be written. Almost the same thing with get API call. So when we want to read blob from distributed storage, we need to gather all the parts of the blobs, but we can, using Erasure coding, we can recover by 4 parts the whole blob data. Let's take a look. For example, we lost 2 drives, and we try to read the data from distributed storage. And we fix all broken devices, but now we have failure on different drives. So we try to read blob parts from all available devices. And we can read 6 parts, or we can read 4 of them and restore necessary data with Erasure. So which operation will be faster, that's quite enough. And one is interesting API call called blog. I want to describe it because master tablet, for example, if we talk about data shard, it has to be only, have to be only single instance of the master tablet within the system. So how we achieve this? There is a special call called blog, and there is special number called generation for each tablet. So each tablet has its own generation, and when tablet born, it has, for example, generation 5 or 1, doesn't really matter. So tablet put a call, bulk API call, and send its generation. And after, and everything works fine. For example, we successfully wrote current tablet generation on distributed storage. And now only 5th generation tablet can deal with storage. So we successfully deal with it, everything works fine, but suddenly something goes wrong. So for example, we lost some part of the cluster in case of partitioning, and tablet has 2 instances, so 2 masters simultaneously on different nodes. Special system component Hive that runs tablet on each tablet restart. For example, if we start new instance of tablet after tablet failure, increase its generation. And now we come to this proxy and said, okay, I have generation 6. We successfully write increased generation number to the storage, but old tablet tried to put its data with old generation, and as far as we successfully wrote a new generation number to the storage, old tablet has an error and decided to destroy itself. So that's how we deal with multiple tablet instances. Okay, that was scalability and fault tolerance and redundancy, but one of the major properties of distributed system is distributed transactions. So what distributed transaction is, it's quite simple. Usually when we talk about distributed transactions, we mean that it's about transactions that deal with data on different servers, but within YDB, as far as we slice tables onto the shards, even transactions that deal with different parts of table is distributed, because there is high probability that different parts of the shard will be located on different nodes. So that was distributed transactions and how to implement this. One of the most popular approaches is two-phase commit, and frankly, we use two-phase commit protocol in many parts of our system. But for distributed transactions, we decided to choose another approach because, as I mentioned, we deal with tens of millions of transactions per second, and pessimistic locking and problems with high contention or high throughput does not allow us to use two-phase commit. So that's why we use Calvin approach. It's a paper from 2012, quite mature for today. And it's about non-blocking execution of deterministic transactions simultaneously. Despite its a new approach, it has its own restrictions, and frankly, we don't use a pure, clear Calvin. We use Calvin with many our own extensions. Okay, let's talk about this. So deterministic transactions, what is deterministic transaction is? It's transaction who knows its read and write key sets on the start. So during the start, transaction know what data it will touch, and thus it's deterministic. But even in single queries transactions, we can deal with non-deterministic transactions, especially when, for example, we deal with secondary indexes. We never know the data we will touch because, first of all, we read data from the secondary index, and then we go to the main table, and we have to deal with the main table, and we don't know key sets that will be touched by our query. So what provides us Calvin? It's about coordinated transaction execution. So for example, within our system, there are data shards, and we have such component as coordinator. And we have a set of transactions. So within coordinator, we have to put all the transactions in strict order and send those order of transactions to data shards. So we will execute simultaneously on different data shards transactions in correct, strong order. And thus, we will have serializability. There are many restrictions of Calvin, as I mentioned. For example, such as only single coordinator system and deal with only deterministic transactions. But as I mentioned, in real world, there are too many very useful but non-deterministic transactions. So we improved Calvin protocol, and we make such functionality as multi-step non-deterministic transactions. We optimize so-called immediate transactions because quite often we can deal with key value queries, and this is not a distributed transaction. This is a single shard transaction, so we can reorder transaction order and we can optimize, we can use happy path for such transactions. How we deal with single coordinator problem? So when we talk about distributed system, every time when something is in single, something is single, every time it's problem, it's bottleneck. So we can use many coordinators. On the picture, there are 2 coordinators, but there could be much more. So it's configurable via cluster. So within each coordinator, we have such called planning quantum. So within each coordinator, for every 10 milliseconds, we gather, we collect all incoming transactions. Transactions could be, there could be different heuristics how transaction choose its own coordinator. For example, closest one within the same availability zone, etc. So it's not a big problem. So each coordinator collects its transaction set. Each coordinator within 10 millisecond quantum is ordering all the bunch of transactions and send it to the data shard. But you can say there are many data shards and many transactions. So if each coordinator sends many transactions on data shard, how it will merge all those transactions. And there could be simple heuristics. So for example, we just can say like first coordinator is first in the order, etc. Moreover, within each quantum, each transaction has its own, now we call it version, but earlier we call it plan step. So each transaction has its own unique ID, and it's a plan step within astronomical time within those quantum of planning. And thus, we can easily merge all the transactions within data shard and guarantee serializable execution within the data shard. How we deal with multi-step transactions, non-deterministic multi-step transactions? we look at all the steps of multi-step transactions as a step of deterministic transactions. And within each step, we take a lock. As far as we have and we choose optimistic locking strategy, we can easily take as many locks as we want, and the fastest transactions wins. So we can easily execute multi-step transaction, taking locks, and in the end, on commit, if there was no problems, transaction finished successfully, or otherwise it will have transactions locks invalidated error. Now let's take a look at one of the final parts. As far as we talk about distributed system, how it looks from client side. So first of all, if we talk about huge throughput, it means that on the client side there is a huge fleet of Docker containers or, I don't know, processes, etc. It doesn't really matter, but you have huge fleet of your applications. And you have, on the other side, you have many application nodes of the database. And both of those systems are very volatile because, first of all, we have to deal with availability zone failure, disk failure, rack failure, or you can want to increase your database, for example, put another 300 application nodes instead of 600. So we want to provide convenient way to deal with database, and that's the reason why we logically divided YDB cluster onto two logical parts, entry points and endpoints. So for your client application, instead of using configuration with hundreds of nodes, you can use only like name with entry point. And for entry point, you can use DNS balancing or load balancers on different OSI layers. And when your application calls entry point, this is the only, during all the whole application lifecycle, this is the only single call when application calls entry point and it executes list endpoints call. It receives list of endpoints of your database, which can consist of hundreds of different nodes. And in recurrent mode, every minute, it will call list endpoints to rediscover each minute a list of endpoints of your database. In order to keep database within in order to keep each of the database node with the same workload, we implement client-side balancing. But despite all the efforts, it doesn't really help. First of all, because client-side balancing is quite hard to implement. And during your application lifecycle, cluster looks exactly as on the picture. So you can't have equally loaded nodes. And due to such problem, we implement server-side balancing. So from the server side, we try to gracefully shut down sessions on overloaded nodes. And that's it. So we try to evenly distribute all the client session between different nodes. Okay. That's it about system details, but just some details about features. We have our own SQL dialect called YQL, quite convenient, very similar to ANSI with convenient DDL, DML operations, many functions implemented. We are working on different user facilities, like we provide SDK for 8 languages. most popular programming languages. Within each cluster, we provide user interface and convenient CLI. And you can easily deploy YDB wherever you want. As far as during our open source release, we provided a Kubernetes operator for YDB. You can ask me, how about benchmarks? But let me introduce you to Evgeny Ivanov. You can join his speak within a couple of hours in this particular hall. So feel free to ask Evgeny about anything you want to know about YDB benchmarking, because he's spending many times while optimizing and benchmarking YDB. Let me remind you that YDB is a distributed SQL database with strong consistency, scalability, fault-tolerant, and fully open source. So where are we going? Where are we heading? Currently, we are working on PostgreSQL, dialect, data types, wire protocol, and runtime compatibility. And as far as this is a huge system with huge workloads and big data, we are currently working on analytical abilities of YDB. Thank you so much. That's it.
All right. Thank you, Oleg. Certainly, thanks a lot for your insights. You thought it's over. No, it's not yet. Now we have another important part here. So first, for all of you here in the audience, if you take a look at your badge booklet, there's a QR code over there for a conference app. You can use it for communicating between your fellow colleagues, also for rating the talks. And the important part, please rate the talk. You have the QR code for that. This provides a feedback back to the program committee, which allows the program committee to select what you eventually like, right? And the better feedback you provide, the better content you get. Now it's time for questions. So please raise your hand, and whatever you wish to know about the internals of the YDB, Oleg can answer that. Yes, here in the front, please.
Hello, thank you for your talk. During last slides, you mentioned about server-side partitioning, server-side load distribution. Probably I missed something. You mentioned that you terminating high load sessions. Do you do this in order to hope that after termination it would reconnect to some other less loaded instances?
Exactly. Thank you for your question. Yes, we are waiting for transactions in flight to be completed within those sessions, so we try to do it gracefully. And we send special code for the SDK, like we are too busy. So SDK decided, so SDK can deal with different codes, and there are many, like within the implementation of SDK retry helpers, we try to provide for the whole operation correct work with the codes. So as far as SDK receives, we are busy. It pessimizes this node, and it works. It creates, it makes session, or it sends queries within different sessions with different nodes, and this particular node is pessimized.
All right. So I can see three more hands over there. So the first one here in the middle, please. Then a little bit up, and then at the very back.
First of all, thank you for an excellent talk and your insight in how you're working. I'd like to know, how do you achieve a correct sequence of transactions with multiple coordinators, and how do you avoid race conditions in that case?
Each coordinator has its own transaction set. So tablet, so transactions decided which coordinator to choose, and there could be different heuristics, like minimum round trip, or if we talk about multiple availability zones installation, so it's like optimal to send transaction to nearest coordinator, for example. So each coordinator works only with its own transaction set.
Thank you.
All right, there was a hand closer to the, yeah, over the gentleman with the greenish shirt, yes?
Thank you for the interesting report. My question about data store. As I understand that data should be located in each node in equal count for good best performance. But what happens if you add more nodes, for example, 1, 2, 10 nodes? What happens in these cases?
I'm afraid I don't get the point. Can you please explain a little bit?
I mean that when you add new data node, the tablet, data store and tablet should be reorganized for the data node, right? Is it correct?
We organize into storage groups, different disks and disk slices into storage groups, but for database, we provide many storage groups. So in case we want to increase database capacity, storage capacity, we add more storage groups. But data itself, data part, is very small. So table, for example, if your table consists, if your table stores petabyte of data, it consists of millions of small tables, each tablet is responsible for, at maximum, for 2 gigabytes of data. And all those tablets, all their data, they will be placed on different storage groups. So we don't try to increase vertically, we increase all capacity horizontally. So, for example, what storage group really is. Let's take a look at solid-state drive of 1.8 terabyte data size. We slice it into 8 parts, and we took, for example, 9 such slices, and we combine it into one storage group. So this particular storage group is responsible for a 1/8 multiplied by 9 storage capacity. So what we have to do if we want to increase those capacity? We add more storage groups. But tablets, so like you have millions of tablets, and yeah, we will choose different storage groups for different tablets. But each tablet is very small. So we don't need to reorganize it.
May I interrupt here a little bit? We are running quite short of time, and that's a really important and interesting discussion. May I ask you then continue that afterwards? We have quite a few of the other questions. So at the very back, please.
Okay, thank you. The question is about the process of testing. What infrastructure is used to test the database, and is it distributed between different data centers? Maybe you test on production. And what about manual and automated tests? Which infrastructure is used for automation? Thanks.
We spent years building an testing infrastructure. Something like Jepson. We have system we call it Nemesis. So besides just testing, like code testing, we built real infrastructure, and we have a set of clusters for the testing purposes, and we each release goes through those clusters and tested with Nemesis. Special testing infrastructure.
Right, excellent. So there was a question at somewhat close to the back center, and then we have a gentleman here at the front in the queue. So if we can have that closer to the back, please. Whoever was raising your hand previously, yeah. So I think the gentleman over there.
Yeah. Hi. Thanks for the talk. So, is there a way to access the a D-proxy API and get a cluster that doesn't use the SQL engine, but the lower level engine instead, and just utilize the distributed data storage?
Perfect question, thank you. Yes, but I ain't sure you need DS proxy API, but yes, you can write your own tablet and deal directly with DS proxy. And we have different APIs, not only SQL. We have special APIs like read table and bulk absurd in order to deal with huge bulk of data. When you don't need transactions, when you don't need SQL, you can put bulks of data directly into storage, yes. And read.
Right. Last question, please. And sorry, I have to close the lines. We have 1 minute left. Go ahead.
Okay. Hi again, me again. One short question. If you were to rewrite YDB from scratch today in 2023, what one thing would you change?
Amazing. I think that the whole team, I hope that the whole team think almost the same. I think we will choose PostgreSQL API. Instead of writing our own SQL interface, I think that we will choose PostgreSQL API.
Just the API. Everything else is perfect.
Exactly.
Well, that sounds as a really perfect discussion to continue in the whole. Now, before that happens, Oleg, you have one last task. You need to choose the best question that earns a prize for.
Only one or
only
two?
one? Only one. So your choice.
I think those gentlemen with the last question.
Right. The most famous question from the most famous gentleman earns the prize. Excellent.